Okay, we're going to have a look at momentum, which is the first section of the mechanics side of Module 4. Now thankfully it's something you've met before at GCSE and it's fairly straightforward. Defined by this equation, momentum is mass times velocity. That is the definition. The momentum of a body is its mass times its velocity. Notice that it's velocity, not speed. That means that momentum is a vector. In the same way that velocity has direction as well as magnitude, so does momentum. It inherits that direction from the velocity. That's very useful to know. What are its units? Well, its units are kilogram meters per second. That's the units of mass times the units of velocity, but they are also equivalent to the units of Newton seconds. You can use either. Now, a change in momentum is called an impulse. And that impulse can be calculated. Well, either you can calculate it by looking at what's the change in momentum, what have I got now compared to what I had originally. That is a change in momentum, but we often just calculate it by looking at force times time. That is the equation for impulse that you're given on your data sheet. Now, this is very useful. This is where we get the units of Newton seconds from, but it means that there's this link between a force and a change in momentum. Now we can rewrite Newton's second law in this form. We can say that Newton's second law, instead of being F equals ma, which you're probably used to, it's actually that F is equal to the rate of change of momentum. Now, what happens to find F equals ma is we just say, well, what happens if the mass is constant? Well, that comes out, and then we've got delta v by delta t, or dv by dt, the rate of change of velocity with respect to time. That's just acceleration, so F equals ma. But this means I can calculate force if I know a change in momentum and I know a time. What's more common is that you actually have to calculate the average force, because it's very, very rare that you end up with a constant force in a collision. This is equal to the area underneath a force time graph. So this area underneath, that there is the impulse. As you can imagine, as force is changing over time, this may link back to other parts of the syllabus where forces can be variable, particularly springs, things that can be stretched or compressed, so that the same object can exert different forces over time as it's stretched. Just bear that in mind. It might be worth having a look back at Module 2 to revise Hooke's law. We then get to this idea of momentum being conserved. Now, it is only conserved if no outside forces act. Now, what does that mean? Well, it basically means that you're looking at a system, a closed system. It might be two colliding snooker balls, and you're saying the only forces that happen in this situation is snooker ball 1 hitting snooker ball 2, and vice versa. The only forces that are being exerted is a force on the black by the red, on the red by the black. They're the only forces. Nothing outside, no friction, no air resistance, no gravitational force pulling them down, none of that. The only forces in this system are between the two objects. Now that is obviously entirely fictional unless you're in a perfect vacuum, but it's a good approximation for a lot of situations. We often make this assumption that there are no outside forces. We say, well, friction is negligible, air resistance is negligible, therefore momentum could be thought to be conserved. And that means you get the very easy equation that momentum before equals momentum after. And it's in these calculations where you need to be absolutely certain that you remember that momentum is a vector, that you include its direction. Because here we're going to have positive and negative momenta of objects moving in opposite directions, and that's really important to include in your calculation. Now, there are two types of interaction that you'll commonly have to deal with. There are collisions, which is basically where something is moving and hits something else that may or may not be moving, and there are explosions. Now, explosions are brilliant because the initial momentum is equal to 0. I've got a lump of something, it's not moving. Oh, it has a momentum of 0. If it then explodes, it's going to scatter things in different directions, but they're going to have a total momentum of 0. So that's the trick to explosions, is remembering that initially there's no momentum. Collisions come under two categories. There are perfectly elastic collisions, which are also perfectly fictional, but we pretend they exist. And in those situations, kinetic energy is conserved. So there is no loss of kinetic energy. Now, if all I'm looking at here is one object, one ball bouncing off a wall, if it's a perfectly elastic collision, the ball keeps the same amount of kinetic energy, so it keeps moving at the same speed, just in a different direction. Obviously, this is again an approximation, assuming that energy isn't being lost anywhere. There are also inelastic collisions. An inelastic collision is just anything where kinetic energy is not conserved. This is far more common. You can have a perfectly inelastic collision where two objects will combine together into one object and move off as one. That would be perfectly inelastic, but inelastic just means not a conservation of kinetic energy. Now that is pretty much all there is to momentum. The difficulty is that they can throw some fairly complex questions at you. They can make this about particles, assuming that you remember some Module 1. They can make it about mechanics from Module 2. They can link it with some of the other places, especially if we've got forces acting here. Well, there's no reason why that force couldn't be caused by a gravitational, electric or magnetic field. So you've got to be really on the ball to work out what forces they're talking about and where they come from.